Math 1332, Chapter 3, Symbolic Logic. Section 3, Types of Statements. Video 6, Variations of the Conditional. This will be the last video in this series for Chapter 3, Section 3. But this one really shines some light on how bad people are with logic, especially conditional statements. Question. Suppose you say to your son, if you don't clean your room, then you can't take the car tonight. Obviously, as a way to get him to clean his room. So, your son cleans his room, then asks for the keys to the car. You look at him puzzled, like, what could you possibly want? He says, you said if I clean my room, I can take the car tonight. Is he right? Did you say if he cleans his room, then he could take the car tonight? Well, obviously, that's not what I said. What I said was this, and he says I said that. But you understand where I'm going with this. I said one thing, my son claims that I said another, but are those two statements really the same? This is one of the reasons why symbolic logic exists. People in general are really bad about equivalent statements when it comes to conditionals. Conditionals. Luckily, we can analyze the situation symbolically to determine if the conditional you said, the top one, is the same, in other words, logically equivalent to the one your son claims you said. Because if they are equivalent, then he's right and you should give him the car, unless you're just going to be a liar, which I wouldn't recommend. So let's attack this symbolically. Let's let P be the statement, you clean your room. Now remember, we're flexible with the subject, so it can be you clean your room or your son saying, I cleaned my room, and we can also be flexible with the verb tense. And Q be the simple statement, you can take the car out tonight. What I said was, if you don't clean your room, then you can't take the car tonight. Let's go ahead and translate that into symbols. First off, it's clearly a conditional. So let's go ahead and write the conditional. The left of it said, you don't clean your room, that's the negation of Q. That is not the negation of Q. That is a negation of P. Then you can't take the car out tonight. That's the negation of Q. So this is what I said. But what does my son claim that I said? And by the way, this is fictitious because I don't even have a son, I have a daughter. My son claims that I said, if I clean my room, so it's another conditional, if I clean my room, that's P, then I can take the car out tonight. That's Q. So we said two different conditionals. One has two negations, one doesn't, but are these equivalent? In other words, we're trying to answer the question, are these equivalent? Well, we have a tool for determining whether or not two statements are equivalent. We simply make the truth table for each one, and then we see if their last columns match. So I'm going to do one fairly quickly here. Obviously, I don't have it set up already. And because it's the last video and because I'm hungry and I've been recording all day, we'll just do this one pretty quickly. I'm not going to type anything. I'm going to draw some lines and stuff. So this, that, we need a couple of negations. All right, this should be enough. All right, one more. All right, and the double line will go here. I'm actually going to do the one that my son said first, or rather the son said first, which was P pointed to Q. So here's our P column, here's our Q column, here's our P pointed to Q column. Shoot, this is just a truth table for conditional. We know that already. The only time a conditional is false is when you break your promise. In other words, when the antecedent is true and the consequent is false. Otherwise, it's true. That's one that we've seen plenty of times. No need to dilly-dally. Now, to do the truth table for the one that I said, we need the two negations first. So we'll go ahead and make columns for negation P and negation Q. And then we could do negation P pointing to negation Q. Well, negation P just changes the truth value in the P column, so false, false, true, true. And negation Q changes the truth values in the Q column, So it's false, true, false, true. And we're doing conditional on that, and we are doing it in order left to right, so I don't need to draw the arrows. So where's the broken promise? Where is the antecedent? Where is this true and this false? And the answer is right here. So that is the only row where we write false. The rest is true. And I know I went through that construction of the second truth table, especially really quickly, but the point of this video is not to remind you how to build truth tables, but what to do with them. Here are the columns for my statement, the one on the right and the one my son said on the left. Do they match exactly? And the answer is they do not. Whereas they do agree at the top and the bottom, they do not agree in the second row and third row. And it only takes one disagreement to be not logically equivalent. So what can we conclude from this? Well, surprisingly to most people, the statements, if you don't clean your room tonight, then you can't take the car tonight, and if you clean your room, then you can take the car tonight, are not equivalent. Most people think they're the same. You said if I clean my room. No, I never said what would happen if you clean your room. I only said what would happen if you didn't clean your room. Of course, I would still let them take the car. But the point is, when you have a conditional, it is saying what happens under a certain condition, hence the name conditional. Under the condition that you don't clean your room tonight, I promise this will happen. I didn't say what would happen if you did clean your room tonight. In general, the statements P pointing to Q and negation P pointing to negation Q are not equivalent. In other words, if you have an if-then statement that is true, negating both halves of it doesn't make that true also. Might be true, might not be true, but they're definitely not equivalent. And this leads us to variations of the conditional. There's actually three ways you can take an if-then statement and twist it and change it to make a new one. The first way is what we just saw. Relative, in fact, let's cover up everything below here just for a second, so it's not in the way. Relative to the conditional P pointing to Q, the conditional negation P pointing to negation Q is called the inverse. It is formed by negating the antecedent and the consequent. In other words, you leave it in the same order, but you take the negation of each half. That's called the inverse. Inverse, negation, negate starts with N. I'm trying to give you a gimmick for remembering inverse negating. Excuse me. Relative to the conditional P pointing to Q, the conditional Q pointing to P is called the converse. Now, here you're not negating anything. You are switching the antecedent and the consequent. So, for example, if we took the one my son claimed I said right here, oops, the one my son claimed I said right here, and we form the converse, it would be, if you take the car out tonight, then you clean your room. So that's what the converse is. You switch the antecedent and the consequent. There's a third variation of the conditional. Relative to P pointing to Q, the conditional negation Q pointing to negation P, left something out, left out the arrow right here. Relative to P pointing to Q, the conditional negation Q pointing to negation P is called the contrapositive. Let's scoot that over a little bit. It is formed by both switching and negating the antecedent and the consequent. And you can see all these things by just looking at the structure of these. Here's P pointed to Q. There they are in the same order, but both have been negated. Here's P pointed to Q. There they are in the opposite order, but nobody got negated. Here's P pointed to Q. Here they are in the opposite order, and both got negated. So if you think of them as actions, inverse is negating. This is my symbol for negating. I don't know why. Turn it upside down, I guess. The inverse you form by negating both halves of the conditional. The converse you form by switching both halves of the conditional. And the contrapositive you form by both negating and switching. Now, there's a little bit more to the story, but just a little bit more. For the previous example, we determined that a conditional is not logically equivalent to its inverse. Truth tables can also show that a conditional is not logically equivalent to its converse. I'll leave it up to you to show that truth table. Sorry, I had a brief interruption there. But, all right, let this sink in before we go any further. Conditional is not, that was supposed to be red. Conditional is not logically equivalent to its inverse. Conditional is not logically equivalent to its converse. We didn't show that, but you could do the same thing we did here by doing a double truth table on this and this. And you would see that the conditional is not logically equivalent to its converse. But the conditional is logically equivalent to its contrapositive, which seems really weird. Because if we have an if-then statement and negate both halves, we get a different if-then statement. If we have an if-then statement and switch both halves, we get a different if-then statement. But if we both negate and switch both halves, we get a logically equivalent statement. And there's two ways to show this. One is to do the truth table, build truth tables for P pointed to Q and negation Q pointed to negation P. Their last columns will match. I invite you to try it. But there's another way that bypasses it using the conditional as a disjunction and the fact that a disjunction is commutative. That basically means an or statement can be read or written in either order. My name is Chris or my name is Stan is the same as my name is Stan or my name is Chris. That's what that means. But what do I mean you can use the conjunction, the conditional as a disjunction? Well, watch this. I think this is pretty cool. We know that P conditional Q, P pointed to Q, is equivalent to, from a previous video, the negation of the antecedent or the consequent. I'm not going to go back to that video. You can go back and watch it. But or is commutative, meaning that when you have an or statement, you can switch the order and it won't change the statement. You can have steak or chicken. You can have chicken or steak. Those are the same statements. Now, if we put this back into a conditional, remember how a disjunction goes back to being a conditional. You negate the first part and you leave the second part alone. That's what we did over here. When we went from here to here, the antecedent gets negated and then the consequent gets left alone. And so when we put it back, the first part becomes the negation of the antecedent and the second part gets left alone. Since all these things are equivalent, then the first and the last are equivalent. I know that was very hand-wavy and occurred out of nowhere, but the important thing that you need to know is the green statement on the top, a conditional is logically equivalent to its contrapositive, and the two statements below, which are partially in red, a conditional is not logically equivalent to its inverse or converse, and of course the definitions that you see up there. To wrap up this video, we're just going to do some examples of writing variations. We'll do in words and we'll also do in symbols. So our mission is to write the inverse, contrapositive, and converse and contrapositive of the following. If I study hard, then I will pass the test. All right. So how would that go? Well, for the inverse, we negate each half. So if I don't study hard, then I won't pass the test. Now, let's assume the original that's highlighting green is true. Must the second one also be true? If you don't study hard, is it a guarantee you won't pass? Not necessarily, you might cheat off somebody. Converse. For the converse, we don't negate anything, but we switch the order. So instead of if I study hard, then I will pass the test, it's if I pass the test, then and we'll fiddle with the verb tense, then I studied hard, since obviously the studying happened before the test. Is that true? Not necessarily. You could pass the test, but not have studied hard if you got lucky or if you cheated. So neither the inverse nor the converse is necessarily true if the original statement is true. But what's the contrapositive? That's where you both switch and negate. So if I didn't pass the test, then I didn't study hard. And that is logically equivalent. Because think about it. If the original statement is true, then it's a promise that's kept. If you study hard, then you'll pass the test. If you didn't pass the test, could you have studied hard? No, because if you studied hard and didn't pass the test, you broke the promise made by the original statement. So the contrapositive is logically equivalent. Again, inverse, negate, converse, switch, contrapositive, both. And we can do the same thing in symbols. In symbols, it's actually pretty easy as long as you remember the actions. For the inverse, you negate each half. If our conditional is negation R pointing to S, what would it look like if we negated each half? Well, to negate a negation, you just take off the negation. And of course, we have to negate the S. For the converse, we switch. So the S moves over here. It won't let me do that. I'll have to cut and paste. And the negation R comes over here. So there's the switch. For the contrapositive, we both switch and negate. And it doesn't matter what order you do them in. Let's negate first. And now let's switch. So if you think of inverse, converse, and contrapositive as actions performed on an if-then, the inverse, you negate each half. The converse, you switch each half. And for the contrapositive, you both negate and switch. Then it's really easy to write the variations of a conditional, whether it's symbolic or whether it's in words.